It's starting now.
Okay, I think I may have left a sign term out in one of these expressions. Let me just remind you what they are. The covariant derivative is the ordinary derivative plus I g over root 2 w plus mu t plus w minus mu t minus plus I g over cosine theta w z mu t3 minus sine squared theta w q plus I-E a mu q. So that's the ordinary derivative there. The covariant derivative. And let's sort of remember that in terms of these, the definition of a weak mixing angle is that cosine of theta w is g over square root of g squared plus g prime squared. And sine of theta w is g prime over the square root of g squared plus g prime squared. Okay, so this means in particular, and as I said, theta w is around 0.233 or so. The right-handed, or the covariant derivative acting on right-handed field is quite simple. It's the ordinary derivative minus I-E sine theta w. I guess the simplest way is write that over cosine theta w, or equivalently sine theta w tan theta w z mu q plus I-E q a mu. So on right-handed, remember the leptons, any field, quark or lepton, is a left-handed field, two left-handed fields, effectively two right-handed fields. When I say two, I mean this is altogether a Dirac spinner with 4 components. Oh, by the way, speaking of Dirac spinners, I assigned a small homework problem, which is essentially an exercise in Cahill algebra, and it's due. I hope you survive. Do you have enough heat where you live?
Yeah.
Okay.
I think code is good, nice. It's code. It's a coffee. It's still
I was sick for like 4 weeks.
Viruses have trouble multiplying at high temperatures. So try to take a warm bath and try to stay warm. Of course, we have some sort of student health here, right?
Yeah, yes.
Yeah, you can go to check.
Yeah, you should go to student health because it could be that what you have is bacterial instead of viral. If it's bacterial, they can cure it in a flash with antibiotics.
Okay.
And if on the other hand it's viral, then you just have to stay warm and drink lots of fluids and get some sleep.
Speaking
Anyway,
again of Dirac spinners, I should send Justin an email because I think I put my homework in his box, but I think he had already taken the homeworks out, so he might. My last homework, so he might have already picked them up before I put mine in there. I'll let him know.
We'll send an email to him and me. Okay, so this is the right-handed. So on right-handed fields, what happens? The only thing that the main interaction is the photon, which of course was known hundreds of years ago. More recently, however, people have realized that there's also the neutral gauge boson, the Z, with a mass of around 90 Ckf. And the coupling then is essentially a quarter times the charge, whereas the coupling to the electromagnetic field is the full charge. Secondly, these charges could cancel to some extent because of this minus sign. This in particular means that the right-handed neutrino, which is the only neutral fermion that we know of, the right-handed neutrino doesn't interact at all. So the right-handed neutrino does not interact. And in the narrowly formulated standard model, the right-handed neutrino doesn't even, well, some people don't even put it in the standard model. On the other hand, for particles with charge, they interact both with the Z and with the W, the right-handed fields. And so what you've got, in other words, is, say you have a charged particle going along, you have here a photon coming along, and the coupling is EQ, but you can also have a Z coming along, and the coupling there is E sine squared theta W over cosine theta W and times Q. Now, of course, you might say, well, gee, these couplings aren't that different. Why didn't we see the W along hundreds of years ago? And the reason is that this W propagator is very short range. So in other words, these interactions, although the W interacts with a fermion, if it hits a fermion, it interacts almost as strongly as the photon. In order to get a W, it has to be emitted by some other process, such as another fermion. And so then for this, the amplitude for this process is essentially E squared sine to the fourth of theta W divided by cosine squared theta W, because there are two couplings there. I'm just doing the Z part. And then the Z propagator, which is Q squared plus mz squared. And so for low energy, where you can forget this term, mz squared is the dominant feature. And by the way, when we neglect mz squared compared to mw squared, that's part of why we can get away in the effective field theory lingo or picture, why we can drop the derivative terms of the heavy field because they don't contribute much there. So what actually happens is you have to add these two diagrams, where this is the photon. Now at high energies, this does start to be important, and at very high energies, say at the LHC, this thing is essentially zero, and so the two terms cancel to some extent because of this minus sign here. Anyway, so that's the simple part. That's the right-handed interaction. The left-handed interaction is more complicated, and I'm trying to see where I wrote that down in detail. I guess it's just here. So the left-handed covariant derivative is then the ordinary derivative plus IE over square root of 2 sine theta W. Now we have W plus mu T plus W minus mu T minus. and then plus I E over cosine theta W Z mu, and then we have T3 over sine theta W minus sine theta W Q plus I E A mu Q. And so that's basically the picture. And now what we've got is you can have, for example, let's say we have an electron going along, and here's an electron, and it could turn into a neutrino emitting a W minus, and so then that W minus, what could it, so let's see, what am I doing here? Let's make this a positron. Then the W minus is absorbed, and we have another nu, in fact, an anti-neutrino go out. So that's sort of one process. But of course, this left-handed thing acts on quarks, all sorts of quarks, and so you can have an up quark go along, turn into a down quark, emit a W minus, and if this is high enough energy so the W minus is real, this could go into a say E minus and an anti-E neutrino. Or it could just be an exchange of a W minus. So there are all sorts of things that can happen there. In particular, this process here is what we call beta decay, where actually that's inverse beta decay now that I think about it. So this is inverse beta decay. The actual beta decay has a down quark coming along, turning into an up quark, then a W plus goes along, and what comes out is a positron and an electron neutrino. So that's when a neutron turns into a proton in a nucleus. So this is ordinary beta decay. And then, of course, there's just ordinary scattering, and the scattering goes with photon exchange, but it can also go with W minus or W plus or Z exchange, and so you can have all these different terms. Any questions? Now, last time we were talking about masses, and what I think I'll just sort of skip what I did last time and just say what one actually does. Suppose you want to give masses to down quarks. And what you do is you have an interaction like this. Q left dagger, H, D right, plus the adjoint term, which would be D right, adjoint, H adjoint, Q left. So here Q left transforms according to SU2 left. H does also, so you have the SU2 group element, the adjoint times the group element, that just gives you the identity, and that's why this also is invariant. And what you do is you multiply this by some constant CD, and this has another constant CD, say a complex conjugate, and then the mass of the down quark then is the absolute value of CD divided by square root of 2 times V, where V is this 246 GeV. I'm always using natural units with C equal to 1. In this book that I've written, I made the mistake of going to real units, ordinary units in some sections, and it's bad. It's a lot of trouble doing that in electromagnetism, but in the case of gravity, it's much worse. Anyway, so what happens here is that one just picks these constants in order to fit the MD. In other words, the absolute value of CD is simply square root of 2 the mass of the down quark divided by V. Of course, the mass of the down quark itself is not exactly an apparent quantity because the quarks are confined, and so you never see them floating around. You can't get a bottle of quarks in a laboratory and put them on a scale and see how much they weigh. And you can't even have a beam of down quarks, which you then put in a magnetic field and see how much they curve. And the problem is that they always appear in colorless combinations, and so it's either quark anti-quark or 3 quarks, and they're surrounded by gluons, and everything is strongly coupled, and so it's something of a theoretical nightmare. The basic thought is that let's see, I didn't write down here, I should have, but you can Google what the latest value for the mass of the down quark is. It's of the order of, I don't know, 4 MeV, something like that. It's small compared to the top quark. On the other hand, the up quark is even smaller, so the down quark is 4, the up quark is around 2. This same term, by the way, this Q left is up left, down left, and but of course there are others. There's the one for the second family, and that would be charmed left, strange left, and then there's the third family, top left, bottom left. So there are, when I say QL, at the moment I'm just talking about the first family. This same mechanism, since the lepton doublet is nu left, E left, this same mechanism can give masses to electrons, and then what we have is minus CE, L dagger, L, H, ER, minus CE complex conjugate, ER dagger, H dagger, L. And so this gives you a mass of the electron of CE over root 2V. And I think I've got the factors of 2 right, but I don't absolutely guarantee it. And let me just announce a generalized extra credit homework problem. If you find any mistakes in the notes, the class notes, and send me an email, you get extra credit. Okay, as I said last time though, for top quarks things are a little bit different. So if you have an e to the I theta dot sigma over 2 H is H prime, then sigma 2 H star, let me get this right now, sigma 2 H star times e HCI theta dot sigma over 2 is sigma 2 H star prime. And so the deal is that sigma 2 H star transforms just like H. So we have two doublets, H and sigma 2 H star. And that means that we can give masses to the up quarks, and the way we do that is minus Cu Q left dagger sigma 2 H star UR. And what H star is, it's H plus, that's a plus, H plus adjoint, which I guess is H minus, and then H0 adjoint. So I guess it's H minus H0 adjoint. So that's what H star is. And so we have that minus Cu bar UR dagger H transpose sigma 2 Q left. And this gives a mass to the up quark of Cu over root 2 V. So these all work out in the same way, and they all have this unfortunate relationships between the coupling constants and the mean value of the Higgs field. And I mean, clearly there's something more fundamental going on, and probably in your lifetime, maybe not in mine, somebody's going to announce an explanation of all these quark and lepton masses in terms of some group theoretic interpretation of things. It may be in terms of effective quantum field theory. In other words, you suppose that things are really symmetrical up at high energies, and you get these mass terms at low energies. I don't know how it's going to work out, but it's the mess that we have here works experimentally, but intellectually it's just sort of a joke. All right, let me get on now to this business of three families. The first family is one, it's up, down, nu, E, and E. The second family is charm, strange, nu, mu, and mu. And the third family, F3, is top, bottom, nu, tor, and tor. And in the notes, these all occur with primes. And what primes mean are, these are flavor eigenstates. And you see, if we only had one family, then this analysis would be the whole story, apart from the fact that we pick these constants in this stupid elementary way where we're not explaining anything. But there's no need for primes here, because with just one family, the mass eigenstates and the flavor eigenstates are the same. But, as you'll see in a moment, when we have three families, then what's involved here is the primes are for the fields that transform simply according to the group transformations of SU2 left and U1 of hypercharge. The hypercharge doesn't cause a problem, it's the U1 that causes, the SU2 that causes a problem. So, So we can think of these as Q1 prime is UD prime, and these are, I'm not going to write them all, but I'll just write a couple of them. CS prime, these are flavor eigenstates. These are things that transform simply under SU2 cross U1. And then L1 prime is new EE prime, again, flavor, and L2 prime is new mu prime. And so now, the problem is that instead of having these very simple terms, which when you look at them aren't that simple either, but they're about to get more complicated. And what I'm going to write down then is a sum ij equals 1 to 3. We're summing over family indexes now. Minus, for the down quarks, we're going to have CDIJ, Q prime adjoint, L for left, I, one Higgs field for the moment, and in fact, in most theories, there's just one Higgs field in the standard model. D prime R, J, and then, just to make the thing remission, complex conjugate, Dij, D prime right, well, if we're going to complex conjugate this, then this is D prime right, J dagger, H dagger, Q left, I, no dagger, prime. I think this, I got the indices a little mixed up here. Okay, so this gives mass terms to the down quarks, the strange quarks, and the bottom quarks. So I maybe should put in this last one. And these terms look like this: V over root 2, sum ij 1 to 3, minus CDij, D prime dagger, well, now I've changed my notation. No, this is right, actually. D prime dagger, left I, D prime, right J. Remember there was a right there. And then the complex conjugate of that is minus C bar D ij, D prime right J dagger, D prime left I. Okay, the notes got straightened out at that point. And we can rewrite that as, again, the sum over I and J minus CD ij, D prime dagger left I, D prime right J minus CD ij bar, D prime dagger right J, D prime left I. I'm actually having a little trouble seeing what the difference is. Is that just the same equation written twice? Okay, for some reason on the notes I had it written twice. So this gives a 3x3 mass matrix, and the mass matrix is the down mass matrix, and it has, if that's the mass matrix, the entry for the ith row and jth column is V over root 2 CD ij. Remember, it's this whole thing that gives you a direct mass. And So what we've got is a 3x3 complex matrix with apparently no structure whatsoever, because these coefficients could be anything. And on the other hand, what we can do is we can do a singular value decomposition. And that gives the masses on the diagonal here of the down quarks. And so sigma d is the mass of bottom quark, 0, 0, 0, 0. Mass of the strained quark, 0, 0. Mass of the down quark. So that's how one understands what's happening here. Is what you do is you have a 3x3 complex matrix that has no, it's not Hermitian or necessarily Hermitian, unitary or anything, symmetric, whatever. But you can always do a singular value decomposition, and that gives the masses on the diagonal. Something that I hope I mentioned a few times in earlier lectures is that the mass of a fermion, the sign of the mass of a fermion does not matter. And in fact, it's almost certainly true that the phase of the, I don't think even the phase matters. Certainly the sign does not matter of the mass of a fermion. So what are the mass eigenstates? The mass eigenstates are d right I is r dagger d ij d prime right j. So the matrix that takes your flavor eigenstates and turns them into mass eigenstates is r dagger, and equivalently the flavor eigenstates are, this is these two are unitary, by the way, so we have L dagger L is equal to R dagger R is equal to the identity. So in the single value decomposition, that's unitary, and this is not simply real, but it's a positive or a non-negative matrix. And so D prime is RD. So a similar thing happens for the up quarks. There what we have is the sum on I and j minus CUIJ, 2 prime dagger left I sigma 2 H complex conjugate U prime right J. Oh, I just will write minus Hermitian conjugate or plus Hermitian conjugate actually. And then what we have are a mass matrix whose ij element now is IV over root 2 CUIJ, and we then write this as a singular value decomposition into LU sigma up, right up, and dagger. So up just means the up is shorthand for upstream tau or top. So that's a singular value decomposition of the up quark mass matrix. And sigma up then is top mass, charm mass, and up mass. And L up and R up are both unitary. And this says then that the triplet of up quarks is R up dagger, the flavor ones, and the flavor ones are R up times the mass one. So no prime means mass eigenstates. And that's consistent with the idea that the important fields are the ones that diagonalize the quadratic part of the Hamiltonian, and those are the mass eigenstates. Okay, so now let's go to what's called the Ckf matrix, in which C is Kabibo and K and M are two Japanese physicists who generalized Kabibo's 2x2 matrix to a 3x3 matrix. Let me get some more chalk. Let's see, without Austin, we have no questions. So somebody must have a question, no?
Not yet. I thought I did when you clarified it.
I'm running out of decent pieces of good chalk. This chalk is very good as a big piece, but the pieces get smaller. Small pieces of chalk are hard to deal with. So let's look at the Ckf matrix. First of all, dr mu, as I wrote down before, is d mu minus IE sine theta w tan theta w, let us say q z mu plus IE a mu q. And let me just write down a question there. So what's happening here is that we would write this way. We would say this is u prime right dagger d right mu u prime right. And now we would convert this to mass eigenstates by using this relation, and this would be u right dagger r up dagger dru ru ur. And now what is this thing? Well, this is a mu. This thing is diagonal in the 2x2 space because Q in other words, when this acts on a neutrino field, it leaves it a neutrino field. It acts on an electron, it leaves an electron, it leaves up quarks, down quarks. And so consequently, this is the same as ur dagger dr mu ur. Similarly, d prime, the down flavor quarks dagger d right mu, whoops, d prime right, this is d right dagger r down dagger d right mu r down mass eigenstates, and then this is just d right dagger d right mu d right. So for the z and the photon, there's no issue. On the other hand, the covariant derivative for the left-handed fields is d mu plus IE over root 2 sine theta w plus mu t plus w minus mu t minus plus IE over cosine theta w z mu t3 over SQ plus IE mu Q. So they're all these terms. And so what's actually going on? Well, what we have here is U prime left dagger, D prime left dagger, and then we have this D left mu, and then we have U prime left, D prime left. And when I'm writing U left prime, what I mean is there are 3 fields here. So this is a 6 vector, and this is a 6 vector. And we can rewrite this in terms of mass eigenstates by saying that, well, it's U dagger left, L dagger U, D dagger left, L dagger V, D, times D left mu LU U left LD D left. Well, the covariant derivative is this thing, and the bottom part doesn't make any difference, but the top part does, because it takes, this thing takes interchanges up and down, and the ups and downs are multiplied by different matrices, LU and LD, LU dagger and D, LD dagger. And so what we can do is we can define new T matrices. We can define a T CKM plus as 0, 0, LU dagger, LD, 0. Or we can write it as 0, 0, V, 0. So I'm writing V as CKM. And similarly, T minus CKM is 0, 0, LD dagger, LU, 0. And that is 0, 0, D dagger, 0. Okay, so that, though, when we've done that, we can now rewrite this thing. And I'll try to stand on my tippy toes. I can try to write this down. Probably not, actually, but I'll try. I E over root 2 sine theta W, W plus mu, T plus CKM plus W minus mu, T minus CKM. That's the important part, because the rest of it is just the same as this. And so the rest of it is plus IE Z mu over, let me just write C for sine, T3 over S, C for cosine, S for sine, minus SQ plus IE A mu Q. Okay, so that's what happens when we finish the analysis, namely that the left-handed covariant derivative is like the original, the one family covariant derivative, except that the T pluses and T minuses take this form, and of course, when we're acting on all 3 families, this thing is a covariant derivative that is a 6-dimensional covariant derivative. And so these T plus and minus CKM matrices are 6 by 6 matrices, which are essentially 0 except for these funny places, a V here and a V dagger there, V and V dagger being 3 by 3 complex unitary matrices. Okay. I seem to have written the same equation twice. So there's another way of writing them, and I guess I'll. So in other words, this whole this is the structure that's tricky. So I'm going to write that structure down, and here's what it looks like. It's UCT and then actually, let me write it this way. Dagger 0 V dagger d mu minus V W plus mu 0, and then UCT DSB. And these are just single. This doesn't have a matrix structure. This is 3 by 3, and this is a 3 by 3, 0. So we can rewrite this as UCT V. Actually, I think there's a mistake in that equation. Let's just leave it like that. So I'm going to have to think about how to rewrite this in a nicer way. But basically what happens is this gets written as UCT V on DSB. So we pull the V out that way, and then if we pull the V out, then this is then W mu plus 0, 0, W minus well, I don't know. What I wrote down, what I wrote down may be right, but I'm not sure. In any event, this is, the deal is that we've got this 3 by 3 matrix called the Ckf matrix. And it has been measured to some extent. It's 9 complex numbers in general, but what you can do is you can choose the phases of the 6, say, quark fields arbitrarily, and that eliminates 6 phases. And then I think the fact that it's unitary allows you to eliminate 2 more phases. But there's one phase that's left. And that one phase, so you can make, so you can choose V to be real 3 by 3 with one phase, or apart from one phase, I should say. or except for. So there's one leftover phase, and when K and M announced this result, which when you think about it isn't all that deep, it just follows from the fact that you have three families. They pointed out that because there was one phase that you couldn't get rid of, that could explain CP violation, which had been observed in hadronic systems. In fact, back in the 1960s, Fitch and Cronin demonstrated CP violation in K-meson decays and the K-zeros, I think. And then it's been seen in other systems since then. And so there's been a lot of experimental work done on that since then. For the leptons, for a while, people just regarded the neutrinos as massless, and in that case, there's no issue with the mass matrix, because you don't have this problem of, you see this matrix here is LD dagger LU. Well, if the up leptons are all neutrinos, and if they were all massless, then you wouldn't have to screw around, wouldn't have to choose their mass eigenstates. You could say the mass eigenstates are the same as the flavor eigenstates. In that case, you don't need an LD at all, or you have an LD and it just cancels. And
what is the dimension of the W and W adjunct?
you mean
What is the dimension of W and W adjunct? W plus
W and W plus and W minus.
What is the dimension?
It's just dimension one. It's just a meson field.
Okay, that's
A
what
gauge measure. It's like the photon, but a negative charge or a positive
I guess
charge.
I'm not understanding our notation, just because if those are, is V 6 by 6? I thought we said the CKM matrices were 6 by 6, or is
This is
it
just
3 by 3?
multiplying a 3 by 3 identity matrix.
Right, so that's a 4-dimensional object there.
No, the zero.
The whole matrix is 6 dimensional.
Oh, we're saying the zeros are
3 by 3.
3 by 3 0. Okay, never mind. We were sure for sure. I just thought for a second that I didn't understand the dimensions.
Does this help at all your cough?
I don't know.
By the way, I once had lunch with some immunologists at NIH.
Oh, yeah.
And, they said to me, if you're eating something and you drop it and it falls on the floor, pick it up and eat it. It'll be good for your immune system.
No,
Unless it fell into something that was, if the floor was dry,
Yeah.
pick it up and eat it. If the floor is wet, throw it away.
I don't know. All I think about whenever I see something like that, the same shoes that are walking on this floor, walk in the Western.
Yeah, and outside.
They took that into account. These are serious, these were research immunologists at NIH, best in the business. Okay, so for lepton masses, for leptons, originally we had no problem, but since they do have masses, one has to go through something that's exactly the same as, or analogous to what we just went through for quarks. Let me now go back to something that I said something about previously, namely effective field theories. And so I'm going to, this I think, all right, here's the crazy thing about neutrinos. They have very light masses. And the three neutrinos, as far as we know, have we know they have masses less than an electron volt. And the next lightest particle is the electron, which is 500,000 electron volts. So there's a factor of 1 million. Now the fact that there's a factor of 1 million So we have, in other words, nu, which is EV, quarks, which go from basically MeV, and the electron is almost an MeV. Quarks go from MeV to basically 200 GeV. So that's quite a gap. This is a gap of 10 to the third, but this is a gap of 10 to the sixth. So there's a double gap there in mass, and in particular, people have worried, why are the neutrinos so light? And of course, we can also ask, why is there such a huge range of quark masses? That's an equally valid question. Another, as I said, equally valid question, I think, is why are people talking about supersymmetry, granularification, and strings when they haven't yet explained why we have three families and what the relationships are and why these quark and lepton masses have, in fact, what the Ckf matrix actually is. In any event, here's a nice explanation of why the neutrino masses might be so light. This isn't necessarily true, it's just, and I'm going to the case of one family for the moment, so we don't have something complicated. And I said something like this before. Okay, the neutrinos are up quarks, and so here this is the lepton doublet, and psi can be a singlet field here. It needn't be a doublet itself. M is a huge mass. And so we imagine that this is a theory at very high energies, and as I said, L is nu E. H is the ordinary Higgs doublet. Well, let's get rid of this field at low energies. We can neglect this. For the same reason that we neglect the propagator of the W when discussing beta decay at the MeV scale. So then L psi 0 is minus M. We can drop the derivatives once and complete the square. And when we complete the square, we get minus G over M, L bar sigma 2 H star, psi minus G over M, H transpose sigma 2 L, and then remainder term, which is G squared over M, L bar sigma 2 H star H transpose sigma 2 L. Okay. Now we integrate over the heavy field, and the first thing we do is we shift psi by psi plus that, and that means that we just integrate that. After the shift, this just becomes minus M psi bar psi. Then the path integral over the Fermi field just gives us a field-independent constant, lots of i's, factors of square root 2, so forth. And in effect, what we are left with in the low energy theory is this remainder term, G squared over M, L bar, sigma 2, H complex conjugate, Higgs transpose, sigma 2, L. And now, if we take the mean value in the vacuum of the Higgs field, this turns into G squared V squared over 2M nu bar nu. And this nu bar nu could be, if the neutrinos are Dirac fields, then this is a Dirac mass term. But it's a small Dirac mass term because in fact, we, in a sense, calculated the constant that multiplies it. It's G over 2M, GV over 2M times V. Whereas previously this was just some constant C. Well, previously we had it like this, square root of 2. So let me write it this way. So this the constant that you need to give the neutrino a small mass is the coupling constant V over M. So this is 246 GeV. This is 246 TeV, or 246, not TeV, but PeV, or something that's 100 or 1,000 times higher, because it's this high energy theory in which we were able to neglect the mass. And then what we have then is either Dirac masses or Majorana masses, because this is also a Majorana mass term if the field is Majorana. Because after all, what nu bar nu is its nu left dagger, nu right dagger, 0, 1, 1, 0, nu left, nu right. And if it's Dirac, the dagger means something, because nu left is nu 1 left plus I nu 2 left. If it's Majorana, the dagger doesn't mean anything because it's just one field, and it's, if you want, you can choose it to be Hermitian by using funny spinners. And so in that case, it's a Majorana mass. What I find a little curious in the literature, the party line is that this works for Majorana neutrinos, and people don't seem to realize it also works for Dirac neutrinos. I don't know. Maybe that they realize it, but just didn't say it in the lecture I heard. The question is, there are all sorts of questions. This area of neutrino physics is being studied from the point of view of cosmology. Cosmology puts a certain limit on the sum of the neutrino masses. I guess we have time for me to do one more thing, which is, well, two more things. So this is one mechanism for a high energy theory. I think this is the nicest mechanism. But, you know, who knows what's actually true. Another possibility is that the actual mass interaction for some reason looks like this. Where you have left, right, and I'm leaving out nu, I'm just talking about neutrinos. And So what is so the ordinary, wait a minute, this can't be right. All right, I've got the labeling wrong. The essence of, or let me give you the essence of the seesaw mechanism and leave out an explanation of exactly what the fields are. The idea is that the mass matrix is a 2x2 matrix with ordinary mass terms of the order of MeV, and then a term of the order of GeV, TeV, or 10 to the 15th, or 10 to the 10th GeV. In other words, some huge mass. If you diagonalize this, you see that the eigenvalues are, it's the determinant, of this matrix, which you set equal to 0 to get the eigenvalues, and this gives you lambda minus m squared equals 0. And so the eigenvalues are lambda squared minus lambda m minus m squared equals 0. So lambda is big M plus or minus the square root of big M squared minus, or rather plus 4m squared over 2. And so if you pull out the m, you get m plus or minus m over 2. And then the square root is 1 plus 4 little m squared over big M squared. And so one mass is big M plus 2 little m squared over m, and the other one is these two cancel, and you get minus 2m squared over m. And as I said to you before, that the minus sign doesn't matter in the mass of a fermion. So this gives you a very light fermion, and this gives you a very heavy fermion. So the idea is there are some neutrinos that are really heavy, and then others that are really light. I've got to get straight what those fields are. I actually took the identification that I gave you from Wikipedia. I forgot what the identification was, and I just grabbed it from the web, and I think that's actually wrong. But the seesaw mechanism, this is the seesaw mechanism that you diagonalize a 2x2 matrix that looks like that. So that gives you a natural explanation of a small mass, and it's the same generically, the same as this generically, but it doesn't provide any physical explanation, because if you just write down a funny 2x2 matrix, that's not explaining anything. Whereas in this picture, you can imagine that there's some high energy theory that you could then describe in more detail, and then you get more information down here. But in any case, it's v squared. It's a coupling constant that's dimensionless, and then v squared over m. And here, what we've got is m squared over big M. So it's the same thing. This is the same thing numerically, essentially, but there's much more content in the effective field theory approach. Once again, the effective field theory illustrates something about path integrals, that they make something really easy, and then they make other things really hard. is that story of Feynman. The story I heard was that he decided he was going to teach quantum mechanics entirely in terms of path integrals, and he did that for about 2 weeks, and then he said, well, let's just do it the standard way. All right, I guess we're done, unless it's a question. All right, let's do